Next, bringing the object closer to place it at point 2f1 causes the image to move further, and it can now be seen at point 2f2. Here also, the image is real and inverted, but its size is the same as that of the object. This type of image formation is used in a terrestrial telescope. Here, a convex lens is kept between the objective and eyepiece. It is called an erecting lens. Here, the image to be erected is positioned at 2f of this lens. As the light rays pass through this lens, they converge to give an erect image of the object at 2f on the other side of the lens. Next, on further moving the object closer to the lens, so that it is positioned between 2f1 and f1, the image will be formed at a point further than 2f2. Here, the image is once again real and inverted, but the size of image is enlarged. In other words, we get a magnified image when an object is placed between 2f1 and f1. The best example for this type of image is a slide projector. Here, the slide is positioned between 2f and f on one side of the lens. As the light rays from this slide pass through the convex lens, we get an enlarged image of the slide on a screen kept in front of it. Next, if the object is positioned at focal point f1, then the incident rays will produce an image at infinity. The image will be real, inverted, and extremely large. You would have seen an auditorium. Do you know what is so special about the spotlights used in an auditorium? In such lights, the light source is kept at focal length of the glass cover, which is nothing but a convex lens. Now, when the light is switched on, light rays from the source pass through this lens, and they tend to travel quite a long distance. Due to this characteristic, they can be effectively used to focus intense light on a person on the stage. And lastly, if the object is placed in between focal point f1 and optical center O of the lens, the refracted rays seem to go away from each other, which means they do not intersect each other. But on producing backwards, these rays meet at S' on the same side of the object. In this case, we get a virtual image of the object, which is erect and enlarged. Such an image of object cannot be obtained on the screen. Rather, it can be observed from the other side of the lens. This is the principle for working of a magnifying lens. Also, in a compound microscope, the eyepiece uses a convex lens where the object to be magnified is positioned between center O and focal point F of the lens. The image obtained as a result of this object position helps us to study several biological specimens in detail. Hence, we have studied how an object kept at different positions with respect to a convex lens produces different types of images. We have also understood how these image formations can be applied for practical purposes using various optical instruments, like burning glass, astronomical telescope, camera, terrestrial telescope, slide projector, spotlight, and compound microscope. Later on, we will study these instruments in detail.